Hi, this is the change of concentration with time and half-life worksheet. So for this first problem, it's important to note that it is a first order gas phase reaction. So we know because it's a first order reaction that the graph of the natural log versus time is going to be the graph that has a straight slope. So if you wanted to go in and graph this, you could, and then have that calculate your slope. But when we did this in class, just kind of um, did some calculations without actually graphing it. So the first thing I did was calculate the natural log of each of these concentrations or each of these pressures and came up with these values. 1 over concentration is for a second order rate law, so I just ignored that. I'm not going to fill that in. So once I have that, I can determine the first order rate constant K, because I know that in a first order reaction, K is equal to negative M. And slope, M, is equal to the change in Y over the change in X. And if we were to graph that, that would be the change in the natural log of concentration versus the change in time. So I can type those values in. So I'm just going to pick 2 spots on my chart. I'm going to pick the beginning and the end because I'm going to assume that that's a nice straight line that connects. So my change in the natural log of concentration would be 3.11 minus 6.22. And then my change in time would be 15,000 minus 0. So if I do my math, let me pull my calculator up here. I've got 3.11 minus 6.22. So that's negative 3.11. And that is going to be divided by 15,000 minus 0, so 15,000. So my answer is going to be at negative 3.11, and we're going to take the negative slope, so at the end I'm just going to make this positive, divided by 15,000. That's a small number. We got there. 1, 2, 3, 4. So 2.07 times 10 to the negative 4th. And then I know that it's a first order, so my unit is just going to be seconds to the negative 1, or 1 over seconds. Okay. Now that I know that K value, I can do some more calculations. So I want to know the concentration at 18,000 seconds, but that isn't in my chart here. So since this is a first order rate law, I can use my integrated rate law for a first order reaction. And I am looking for the concentration here at 18,000 seconds. So to do this, this is what I'm looking for. I'm just going to copy that in. So my negative K, so that's my 2.07 times 10 to the negative 4th, times my T time, and I want to know at 18,000 seconds, and then plus the natural log of the initial concentration, which is right in my table here. That's my 6.22. Here. So I'm going to do my math again. I'm going to take 2.07 times 10 to the negative 4th, or 0.000207, times 18,000, and I'm going to put that negative in there, plus 6.22. And that is going to give me a concentration that's the natural log of the concentration. So I don't want the natural log of the concentration. I want to know the actual concentration. So what I'm going to need to do is then undo the natural log. And to do that, you're going to take the inverse log, which is this button here. So I'm going to do the inverse log of that value, and I get 12.1 for my answer. The concentration of CH3 and C is 12.1 molar. So let's look at this. This is decreasing here. So from 12,000 to 15,000, so 3,000 seconds here, it about halved. And then if I go down again, 15,000 to 18,000, I would expect it to be about half of the 22, and 12 definitely meets that. So that makes sense. So then the last step is half-life, and this is a first order reaction. So this is going to be the half-life equation that we're going to use. In a first order reaction, the half-life doesn't depend on the initial concentration. So we're literally just going to take 0.693 divided by the K value. And our K value back up top was 2.07 times 10 to the negative fourth. Okay, so pull my calculator back up. And I'm going to take let's clear this. 0.693 divided by 0.000207. And I get 3,348 seconds. So remember, definition of half-life is half of the concentration, so the time it takes to get to half the concentration. So if our initial concentration is 500, half-life is about 250. So it would be in between these two concentrations here, which means it's going to be in between 2,000 and 5,000 seconds. And that's right where 3,348 falls. Hope this is helpful. This is going to be similar to one of the problems on the review sheet, where you'll have to calculate a concentration using the first order rate law and then also the half-life.